Right now, far beyond the blue glow of Earth, something is misbehaving. An object the size of Manhattan is racing around the Sunday. A wave of solar plasma powerful enough to fry satellites slams into it. By normal comet physics, it should shatter, flare, and veer off course. Instead, its path stays straight and its brightness barely changes. It shrugs off the storm and just keeps going. Astronomers are staring at their screens asking what this thing is. Stay with me, tap subscribe, because this mystery of 3i Atlas could rewrite how we think about the space between stars. Picture the scene. About 130 million miles from Earth, roughly 200 million kilometers, a compact mountain of ice and rock dives in toward the Sunday. It moves at speeds that make airliners look frozen in place, hundreds of thousands of kilometers per hour. Around it hangs a glowing cloud of gas and dust, the classic cloak that makes comets look like ghosts in telescope photos. This should be one of the most fragile objects in the inner solar system, a frozen relic that only recently woke up under the sun's heat. Now imagine the sun losing its temper. Our star does not just shine, it sometimes throws tantrums. In a coronal mass ejection, the sun ejects a bubble of plasma and magnetic field, a billion-ton cloud of charged particles hurled into space at hundreds of kilometers per second. When one of these storms hits Earth, it can induce currents in power lines, disrupt radio communication, and threaten satellites in orbit. All of that happens from 150 million kilometers away. This time, the target is not a planet with a magnetic shield. It is 3i Atlas, a visitor from another star system that has wandered into the blast zone. As the comet reaches its closest point to the sun, instruments on and around Earth watch a massive solar storm barrel straight toward it. This is not gentle solar wind, this is the fire hose turned to maximum. From the point of view of the comet, it is like having the sky itself suddenly turn into a river of charged particles slamming into your face. If you were writing the script based on what we know about comets, you would expect chaos. These objects are not solid iron cannonballs. They are porous, layered mixtures of ice, dust, and fragile rock. When comets skim close to the sun, even without a solar storm, they often crack apart, shed enormous clouds of material, or simply fade away as coherent bodies. They are famous for dramatic breakups, not quiet resilience. That is why the observing teams are tense as the plasma cloud closes in. For days they have tracked 3i Atlas diving inward, watched its coma brighten and its tail stretch. They have run the numbers on what this particular solar storm did to the solar wind around it and how much energy is packed into that wall of plasma. The expectation is not that the comet will explode in a cinematic fireball, but that its behavior will change. A shift in brightness, a kink in the tail, a tiny nudge in its trajectory. Something. Then the data arrive. The storm sweeps over the region of space where 3i Atlas is passing. Instruments that monitor radio signals and scattered sunlight pick up only the faintest trace of the comet. The phrase that appears in one Russian team's report is exceptionally weak signal, the kind of wording scientists use when they are choosing every word with care. But when they compare positions before and after the impact, the result lands like a quiet shock. The trajectory has not changed. Within the limits of very precise measurements, 3i Atlas is exactly where gravity alone says it should be. No measurable shove from asymmetric outgassing. No sign that parts of the nucleus have broken off and wandered away. No obvious flare-up in dust production that would mark a violent rearrangement of its surface. From the cold eye of orbital mechanics, the comet has taken a punch to the face and not even blinked. This is the paradox that opens our story. A supposedly fragile interstellar ice ball behaves more like a well-engineered spacecraft than a crumbling snowball. Its structural integrity seems far beyond what standard comet models would predict for an object that has drifted between the stars for billions of years. Scientists can offer possible explanations, but each explanation drags new questions into the room. Is its nucleus unusually dense and cohesive? Did we misunderstand how solar storms interact with comets? Did we simply get lucky with geometry and timing? To untangle that knot, we need to step back from this single dramatic moment. 3i Atlas did not appear out of nowhere, and this solar hit is only one chapter in a story that began the night a network of robotic telescopes noticed a faint moving dot that refused to fit a neat orbit. In the next part, we will rewind to the discovery, to the first hint that this was not just another long-period comet, but the third confirmed visitor from beyond our sun's domain. To understand why that solar storm encounter matters, we have to rewind to the night this visitor first appeared in our data. On a quiet shift in mid-2025, one of the automated sky surveys that spends every clear night scanning for rocks that might one day hit Earth picked up a new moving dot. The system is called the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short. It does the same thing over and over. Take wide-field images of the sky, look for any tiny speck that shifts its position against the background stars, then flag those specks for follow-up. On most nights, the software finds nothing more dramatic than another small asteroid in a very large catalogue. This time, the motion did not fit. Imagine the sky as a fixed wallpaper of stars. Survey telescopes, take a snapshot, wait a few minutes, then take another one of the same region. If a faint object has moved slightly, automatic, software subtracts one image from the other and highlights a little dot that has shifted. Humans then measure that shift very carefully and turn it into a rough orbit. Most of the time, the first attempt at an orbit comes back as an elongated loop around the Sunday. It might cross Earth's path or Mars or stay out in the main asteroid belt, but the math says it is bound to our star. Gravity has it on a leash. When astronomers began to plug the early measurements of this new object into their orbit-fitting programs, they saw something else. The curve that best fit the data was not a closed oval, but an open hyperbola. That is a shape that means the object is passing through once and then leaving forever. The sun will bend its path, but not capture it. In the language of celestial mechanics, the object has more than enough speed to escape the sun's gravity well. That is why it earned the label Interstellar. It did not grow up here. It came from the space between stars. We have only seen this kind of visitor twice before in modern astronomy. In 2017, a strange elongated object swept inside the orbit of Mercury and then slingshotted out. It was named Oumuamua, a Hawaiian word often translated as scout or messenger from afar. It did not sprout a visible tail like a classic comet, yet it accelerated in subtle ways that hinted at some kind of outgassing or other force at work. Then, in 2019, a second visitor arrived, this time unmistakably comet-like, with a bright coma and a tail of dust. That one was named Borisov, after the amateur astronomer who discovered it. It behaved very much like a normal comet, just one that happened to come from another star system. So, by the time survey software added a third interstellar candidate to the list, astronomers had a simple mental picture ready. Oumuamua was weird and dry, Borisov was wet and ordinary, and this newcomer, later labelled 3I Atlas, might be something in between. Still, the basic story felt familiar. An interstellar wanderer had been nudged by gravity into our neighbourhood, and we had a brief window to study it before it vanished back into the dark. But as more observatories turned their mirrors toward the newcomer, the sense of routine began to fade. First came the realization that 3I Atlas was big, somewhere between 2 and 6 kilometers across based on how bright it appeared and how diffuse its coma was. That size range means a lot of mass, tens of billions of tons, not just a pebble from another system, but a small world in its own right. Then came the speed, roughly 210,000 kilometers per hour relative to the Sun, one of the fastest objects we have ever tracked in our inner system. Only some long-period comets that dive almost directly into the Sun move faster, and they are gone again almost as soon as we notice them. The combination of mass, size, and speed made 3I Atlas immediately important. A chunk of rock and ice, that large carries enormous kinetic energy. Thankfully, its hyperbolic path never comes anywhere near Earth, but as soon as the interstellar nature was confirmed, planetary defense teams paid attention. You want to understand any class of object that might occasionally cross your orbit with that kind of momentum behind it. At the same time, something more subtle was happening in the background. Researchers remembered how much debate followed Oumuamua. Some argued for exotic explanations involving very low-density materials or sheets of ice. Others proposed that it might even be a piece of alien technology. That controversy had taught the community a lesson. When you get the rare chance to watch a visitor from another star up close, you gather as much data as you can, as early as you can, and you watch for anything that does not fit the standard comet and asteroid playbook. 3I Atlas quickly began to reward that cautious curiosity. Even before it swooped past Mars and took the solar punch we saw in Part 1, spectrographs were hinting that this was neither a boring copy of Borisov nor a twin of Oumuamua. Some of the first oddities came from the way it brightened and the distances at which it started to shed material. Those clues pointed to an object that woke up earlier and more violently than our familiar comets, as if it carried a different blend of ices under its surface. By the end of those first weeks, one thing was clear. This third interstellar visitor was not going to slip quietly into the catalogue. It was large, fast, and active, on a path that would bring it close to multiple planets. It was the kind of encounter you plan your observing campaigns around, the kind where every new telescope that joins in might catch a detail no one else sees. And one of the most dramatic chances to see it up close would arrive not long after discovery, when it brushed past Mars so closely that a camera in orbit could have photographed its surface in remarkable detail. Soon after the interstellar status of 3I Atlas became clear, the universe handed us a gift. The object was on course for an impossibly close pass by Mars. Not close in the poetic sense, close in the way that makes engineers grip the edges of their desks. On a morning in mid-October, the comet raced past the red planet at a distance of around 12 miles, only about 20 kilometers. Many communication satellites around Earth orbit much higher than that. This was not a casual drive-by. It was a near rendezvous. Orbiting Mars at that moment was one of the sharpest cameras humanity has ever put into deep space. The high-resolution imaging science experiment, better known as the HiRISE camera on the Mars Reconnaissance Orbiter, was built to photograph Martian craters and boulders at scales where each pixel covers less than a meter. It can spot tracks left by rovers and even hardware dropped during landings. Now, that same instrument had a chance to aim at something from another star system zipping past, just a few planet-sized body lengths away. Think about what that alignment means. For almost every interstellar object in history, we have been limited to tiny points of light, a handful of pixels on even our best telescopes. We infer shape, spin, and composition from how that point brightens and fades, or from the way its light splits into colors. With 3I Atlas near Mars, we suddenly had the possibility of literal photographs, images where the nucleus would span many pixels and surface details might be distinguishable. Cliffs, jets, color variations, perhaps even layers exposed by recent fractures, all potentially visible through that camera. The observing plan was ambitious. As 3I Atlas approached Mars, mission teams calculated the geometry of the flyby, working out when and where the HiRISE camera should point to catch the interstellar traveler as it flashed past. There was a narrow window where the spacecraft, the Comet, and the Sun would all line up just right. Miss it, and the chance would be gone forever. Hit it, and we would have the closest direct look at a body from another star that our species has ever achieved. After the pass, we know that data were recorded. Internal reports and public comments make it clear that the HiRISE team successfully observed the comet. Scientists who have seen the raw images describe them cautiously. They mention jets, surface features, and structures in the coma that could yield new insights into how the object is shedding material. The way they talk is careful, professional, and just a little bit tantalizing. In principle, images from that mission normally flow into public archives on a routine schedule. That is part of how planetary science works. Data are shared so that anyone with expertise and curiosity can analyze them. Yet as weeks turned into months, those specific frames did not appear in the usual databases. Instead, references to them in scientific talks and conference abstracts used a specific phrase. The images are under internal review. That is not unheard of. Sometimes teams need time to verify calibrations or correct processing artifacts before releasing high-impact data, but the longer the delay stretched, the more it stood out. These are not pictures of an old crater on Mars. They are the clearest views of an interstellar object ever recorded, and they could help resolve some of the very anomalies puzzling observers on Earth. This is where the tone of the story shifts from pure wonder to a more uneasy curiosity. Officially, no one is saying the images show anything impossible. They hint that careful analysis could reveal more about localized jets, about how gas and dust escape from particular vents on the surface, about how sunlight is being absorbed and radiated. Unofficially, the choice of wording matters. When scientists say that data could reveal something, they are not usually talking about a shot in the mad, dark. They are talking about a pattern they already see, a pattern they are not ready to name. It is important not to fall into easy conspiracy thinking. Space agencies move slowly. Reviews take time. There are real concerns about not overinterpreting early images, especially when the world is watching and speculation about alien probes is already swirling online. But it is also fair to notice that the most detailed evidence we have of this object is still bottled up. We have its overall brightness, its spectrum, its orbit, its reaction to a solar storm. Yet the pixel-by-pixel portrait from the Mars encounter remains hidden behind institutional caution. For the moment, that gap does something interesting to the narrative. It turns the Mars flyby from a solved chapter into a cliffhanger. We know the pass was close. We know the camera was capable. We know data were taken. We do not yet know what those images really show. That absence forces us to lean more heavily on the other lines. Of evidence we do have, the ones that have already started to bend our understanding of 3I Atlas in strange directions. One of those lines comes from the chemistry of the coma itself, the ghostly atmosphere that surrounds the nucleus and glows with the fingerprints of whatever is boiling off into space. And that chemistry, as we are about to see, is every bit as strange as the missing photographs. To see how strange 3I Atlas really is, we have to stop looking at the silhouette of the comet and start listening to its light. Around any active comet, there is a hazy envelope of gas and dust called the coma. Sunlight passes through that cloud, and specific atoms and molecules absorb and re-emit energy at very particular colors. When astronomers spread that light into a spectrum, they get a barcode of bright and dark lines, a chemical signature that lets them say what the comet is made of, even from hundreds of millions of kilometers away. When the Very Large Telescope in Chile turned its spectrographs toward 3I Atlas, the team expected the usual suspects. Maybe some water vapor, maybe some sodium or other common elements, maybe a handful of trace gases. Instead, they saw something that made them go back and check the instruments. The spectrum showed glowing nickel vapor, a clear and unmistakable sign that nickel atoms were present in the gas around the comet. That would already be impressive for a comet that far from the Sun. Then came the real shock. The signal from iron was missing. In planetary science, nickel and iron behave like a bonded pair. They form together in the hearts of stars, condense together in protoplanetary disks, and are found together in meteorites, asteroids, and cometary dust. When one appears in a gaseous state around an object, the other is usually not far behind with similar strength. Here, though, 3I Atlas was shedding nickel vapor with no parallel iron signature. It was as if smoke were rising from a fire, but every test for soot came back empty. The temperature math made things even weirder. Nickel has a boiling point close to 3,000 degrees Celsius. At the distance where those observations were made, several times farther from the Sun than Earth, the sunlit side of the comet should have been at roughly minus 100 degrees Celsius, give or take. There is simply no straightforward way for bulk nickel metal to be heated to thousands of degrees on the surface of a small, spinning, airless body that far from the Sun. You do not accidentally bridge a temperature gap of almost 3,000 degrees. One proposed explanation is that the nickel is not sitting in the nucleus as lumps of pure metal. Instead, it might be locked up in fragile molecules or minerals that break apart easily under ultraviolet light from the Sun. In that scenario, the energy required to free nickel atoms would come from the splitting of chemical bonds, not from heating the material to its boiling point. It is a clever hypothesis, and it keeps the laws of physics intact. The problem is that no one has actually identified such compounds in comets before. They exist as mathematical possibilities and lab curiosities, not as well-documented ingredients of icy bodies. The answer solves one puzzle only by opening several more. While researchers were still arguing over the nickel, the James Webb Space Telescope added another twist. Webb observes in infrared wavelengths, where it can pick out the spectral fingerprints of common cometary ices with exquisite sensitivity. Pointed at 3I Atlas, it returned a result that flipped decades of comet lore on its head. Instead of seeing water as the dominant volatile, with carbon dioxide and carbon monoxide as minor extras, Webb saw the opposite. The gas around the comet was rich in carbon dioxide, with water playing the supporting role. In a typical solar system comet, water ice makes up 60 to 80% of the volatile material that turns to gas as it approaches the sunday. Carbon dioxide is usually a trace component. You can think of ordinary comets as dirty snowballs, with a lot of water and a sprinkling of dry ice. 3I Atlas reversed that recipe. It looked more like a block of frozen carbon dioxide with some water mixed in. That composition points to a formation environment that was far colder than the region where our comets grew, an outer zone of some distant stellar system where only the most easily frozen gases could solidify. Combine those facts and the picture gets stranger. We have a comet whose gas cloud is dominated by carbon dioxide rather than water. We have glowing nickel vapor without the expected iron signature. We have activity starting at distances where most comets are still asleep. Each of those anomalies could, in isolation, be shrugged off as an oddity. Together they suggest that 3I Atlas is not just a familiar object dropped into an unfamiliar orbit. It is a genuine, alien, chemically speaking, a relic of a star-forming region with different temperatures, different pressures, and possibly a different mix of heavy elements than our own. The chemistry of the coma is not just a curiosity for experts. It feeds directly into the central mystery of how this object behaves. The kinds of ices that dominate the nucleus determine when and how strongly it wakes up, how powerful its jets become, how its tail forms, and how sensitive it is to sunlight at various distances from the sunday. If 3I Atlas is running on a carbon dioxide-rich fuel mix with exotic nickel-bearing components, then its entire response to solar heating will be out of step with our expectations based on water-heavy comets. That might explain some of the early activity. It does not yet explain why a body that formed in such extreme cold and has spent billions of years in interstellar deep freeze is so violently alive now. That paradox is where we turn next. Once you accept that 3I Atlas is chemically odd, the next question practically forces itself into your mind. Where did this thing actually come from? Comets are not random lumps of ice. They are time capsules from the places where they formed. The balance between water, carbon dioxide, carbon monoxide, and heavier elements is shaped by the temperature and density of the disk of gas and dust around a young star. When Webb shows us a comet whose gas is dominated by carbon dioxide, that is a clue that its birthplace was brutally cold, much colder than the region where most of our comets assembled. In our own solar system, water ice can freeze solid in the outer planet region, so bodies that form beyond Jupiter and Saturn tend to be water-rich. Carbon dioxide, on the other hand, needs lower temperatures to lock into solid form. It prefers the deep freeze of the far outer disk. If 3I Atlas carries more carbon dioxide than water, that suggests it formed in a zone far from its parent star, A, regions so cold that even carbon dioxide could collect into ice. Some researchers have gone further and argued that the conditions implied by its composition might be colder than anything in our own Kuiper belt, out beyond Neptune. Then, there is the age question. When teams modelled the likely formation environment that would yield such a mixture of ices and heavy elements, they landed on scenarios that go back to the early days of our galaxy. The idea is that 3I Atlas might be one of countless objects born in the first few billion years after its home star lit up, then flung out of that system by gravitational interactions with giant planets. It could have been wandering between stars for ages longer than the entire history of life on Earth. Some estimates even suggest that it might predate the formation of our sunday. That means it could have been drifting in the dark when our solar system was still a flat disk of dust. If that picture holds, you would expect an object like this to be exhausted. Imagine billions of years in near absolute zero, with only faint starlight and the occasional brush with thin gas to disturb it. The surface should be hardened, processed by cosmic radiation, sealed under a crust of material that has been baked and refrozen many times over. By the time it falls into our solar system, you might think of it as an ancient fossil, more dead than alive, slow to wake up even under the growing glare of the sunday. Instead, observations show the opposite. 3I Atlas turned on early and with enthusiasm. At distances of 3 and 4 astronomical units, where many comets are still little more than dark rocks, it was already releasing water vapor, carbon dioxide, carbon monoxide, and even cyanogen gas. Spectrographs at telescopes like Gemini South picked up these signatures at ranges where models say only the most volatile ices should be stirring. Here, a supposedly ancient and deeply frozen visitor was behaving like a young, caffeinated comet that cannot wait to start boiling. There is a simple way to state the paradox. The more extreme and ancient its birthplace, the more frozen and inert it ought to be today. Yet the colder and older we infer its origin to be, the more flamboyant its activity becomes under our Sunday. Scientists have sketched out possible answers. A carbon dioxide-rich mix will start to sublimate at lower temperatures than water ice, so a comet loaded with that material can indeed awaken farther out. Perhaps the structure of the nucleus includes deep pockets of pristine ice connected to the surface by fractures, allowing gas to escape more easily. Or maybe previous passes through other stellar systems have cracked the crust in ways that now act like nozzles, focusing and amplifying outgassing once it starts. Those explanations are not impossible. They are reasonable guesses built on what we know from comets in our own system, adjusted for a different chemical recipe. The catch is that every time you tweak the model to explain one odd behavior, another quirk of 3I Atlas pops up that forces you to adjust something else. Early activity might be explained by carbon dioxide richness, but that does not directly address the nickel vapor with no iron, or the way some of its jets seem to behave at particular angles to the Sunday. Each fix leaves loose threads hanging. From a distance, the effect on the scientific community is almost psychological. People who study comets are used to them being messy, unpredictable, and prone to surprises. Yet there is a difference between an object that is chaotic in familiar ways and one that seems to be breaking the unwritten rules of the game. 3I Atlas, with its likely ancient age, its ultra-cold formation zone, and its over-eager activity, is not just noisy data. It feels like a challenge to the assumptions built into our models. The very fact that such an old, cold object can be this alive undercuts the comforting idea that long travel times and deep freeze environments always mean quiet behavior. That tension primes us for the next chapter in its story. Because if the chemistry and the timing were not enough to stretch our sense of normal, the way 3I Atlas throws out material into space pushes things even further. When astronomers began to map its tail, they saw something that seemed to point in the wrong direction. A feature that first looked like a trick of perspective and then started to move in ways that raised much stranger possibilities. From a distance, comets all look like the same simple cartoon. A glowing head near the sun and a tail streaming away into the dark. Solar radiation and the charged particles in the solar wind push gas and dust outward, so the tail should always point roughly away from the sun, no matter which direction the comet is actually traveling. It is one of the basic rules you learn in any introductory astronomy class. That is why what happened next with 3I Atlas caught so many eyes. Its tail did not seem to be obeying that rule. In late September, the Nordic Optical Telescope and several other observatories took long exposure images of 3I Atlas. When astronomers processed those frames, they saw a distinct spike of brightness, pointing almost directly toward the sun instead of away from it. This structure was not a faint blur at the edge of detectability. It was a sharp, well-defined feature. To anyone used to textbook comets, the image looked like a mistake, as if someone had flipped the direction of the sun by accident. The term that describes such a configuration is anti-tail, a tail that appears to point backward. Now, anti-tails are not completely unheard of in comet science. There is a well-known geometric trick that can make dust ejected earlier in the orbit appear to form a spike that points the wrong way when seen from Earth. Imagine the comet laying down a trail of slow dust particles along its path. When our planet crosses the plane of that orbit, we can end up looking almost edge-on at that dust lane. In that special viewing angle, particles that were left behind can line up in our sight and create what looks like a tail that points toward the sun, even though the physics is still pushing material outward. So the first reaction among many scientists was to reach for this explanation. Perhaps 3I Atlas had ejected a lot of dust earlier, and the Earth-Sun comet geometry had just happened to move into the configuration needed to produce an anti-tail illusion. For a little while, that was a comfortable story. The universe could look strange while still behaving normally. But then, observers kept watching. They did not see a static feature that just sat there while the viewing angle changed. They saw something that evolved. Over days and weeks, that sunward-pointing feature grew stronger, then began to rotate. By late September, telescopes recorded the structure bending, and gradually, transforming into a more conventional tail that pointed away from the Sunday. In other words, the apparent anti-tail did not simply wink in and out as our line of sight shifted. It behaved like a physical structure in the coma, reorienting itself in a way that tracked the comet rather than the Earth. That pattern made some people uneasy, because it was harder to sweep under the rug of perspective tricks. At this point, a familiar name enters the story. Avi Loeb, a former chair of the astronomy department at Harvard and someone already known for pushing bold ideas about interstellar objects, took a close look at the anti-tail data. In his analysis, he argued that the sequence of appearance, strengthening, and rotation did not line up neatly with a simple model of spin-driven outgassing plus geometry. Instead, he suggested that the behavior resembled controlled maneuvering, the kind of gradual vector change you might expect if gas jets were being used deliberately to adjust an object's orientation and trajectory. That is a loaded suggestion, and Loeb knew it. He did not stand up and declare that 3I Atlas is a spacecraft. What he did say is that when you see an interstellar object with multiple anomalies, you should keep the possibility of artificial origin on the table alongside natural explanations. In his view, the evolving anti-tail belonged in that pile of anomalies. If we ever were to encounter a disguised probe that used comet-like jets for steering, its behavior might look something like this. Rather than dismiss that thought out of hand, he urged the community to treat it as one option to test. Most astronomers pushed back. They pointed out that comets are notoriously finicky. Small changes in the orientation of spin axes, patchy distribution of volatile ices, and complex interactions between gas flows and dust particles can produce tails and jets with intricate shapes. They built models where a naturally rotating nucleus with asymmetric venting could produce an evolving anti-tail without any guiding intelligence. On top of that, Occam's razor remains a powerful tool. Given a choice between an unusual comet and a covert alien probe, the safer bet is still the weird comet. Yet even the skeptics admitted that this particular case was a challenge to model cleanly. You could fit part of the behavior, but not all of it, or you had to fine-tune the spin rate and vent locations in ways that felt contrived. Once again, 3I Atlas was forcing people to work harder than usual to keep everything within the boundaries of normal behavior. And because it was already odd in its chemistry, its early activity, and its resilience under a solar storm, the anti-tail did not land as an isolated curiosity. It landed on top of a growing stack of questions. For a viewer following along, this is the moment where imagination and caution collide. On one hand, there is a very human desire to seize on any hint of pattern and shout that we have found evidence of something engineered. On the other, there is the long track record of the universe being stranger than we thought, but still fundamentally natural. 3I Atlas sits right at that crossroads. Its shifting tail invites wild speculation, even as most of the field insists that better comet physics, not technology, will eventually explain it. Whether you lean skeptical or speculative, the anti-tail episode changes how you watch the rest of the comet's journey. From now on, every bend in its path, every jet, every flare-up is read not just as a data point in comet science, but as a possible clue in a larger puzzle. And there is another layer to that puzzle, because the path 3I Atlas is following through our solar system looks, in a few important ways, exactly like the kind of path we would design for our own spacecraft if we wanted to study the inner planets with maximum efficiency. When you plot the path of 3I Atlas through our solar system, it does not look like the random skid of a rock that just wandered too close. It looks like an itinerary. On the charts that mission planners use, the thin curve of its orbit snakes past the major players in a sequence that feels almost choreographed. First, a deep pass by Jupiter, the king of the planets. Then a swing toward Venus. Then a brush with Mars. Finally, a slide back outward, crossing the paths of the giant planets again on its way into the dark. For a moment, forget the mystery and think like an engineer. If you wanted to design a spacecraft to survey our inner system without carrying huge amounts of fuel, you would lean on gravity. Real missions already do this. They dive past planets to steal a bit of orbital energy, changing their speed and direction without firing a rocket. It is called a gravity assist. The famous Voyager probes used a rare alignment of the outer planets to line up a series of slingshots. a grand tour that let them visit Jupiter, Saturn, Uranus, and Neptune in one go. The path of Three-Eye Atlas evokes that same idea on a larger stage. Here is how the physics works in simple language. A small object approaches a planet that is in motion around the Sunday. As it falls toward the planet's gravity well, it speeds up. As it climbs away again, it slows down relative to the planet, but not necessarily relative to the Sunday. Depending on the geometry of the encounter, the object can leave with a new direction and a different speed in the heliocentric frame. From the point of view of the Sun, the planet has either given up a tiny bit of energy or taken some away. For a spacecraft, that effect is gold. It means you can use the mass of worlds as part of your propulsion system. Now, lay that understanding over Three-Eye Atlas. The interstellar object comes in on a hyperbolic path. Long before it is publicly famous, astronomers run forward simulations to see where it will go. They find that its trajectory threads past Jupiter at a distance that lets the giant planet bend its path just enough to send it inward. That bend sets up a later encounter with Venus, which in turn shapes the later pass by Mars. Each encounter is distant enough that there is no danger of impact, but close enough that the combined effect is a graceful loop through the inner system's major gravitational anchors. Is that special? In one sense, no. The solar system is a messy gravitational field. Interstellar objects arrive with all kinds of incoming directions and speeds. Many will zip through the outer regions and leave without ever coming close to a planet. Some will dive inward on paths that happen to skim near a giant world and be flung away in a different direction. A small fraction will stumble into sequences of encounters that mimic the kind of grand tour trajectories our mission designers love. From a statistics point of view, given enough interstellar visitors and enough time, neatly nested flybys are bound to happen. In another sense, though, the path of Three-Eye Atlas nags at the imagination. It does not skim one planet and leave. It appears to sample several in an order that gives a rich cross-section of the Sun's domain. Jupiter, with its massive magnetic field and hordes of moons. Venus, with its thick atmosphere and proximity to the Sunday. Mars, with its thin air and dusty surface, plus whatever hardware we have placed in orbit there. If you were drawing up a tour for an automated surveyor that wanted to taste different gravitational environments, different solar wind conditions, and different vantage points on Earth, you could hardly do much better without fine-tuning. Most scientists stop themselves there. They will say that the elegance of the path is interesting, perhaps even convenient, but not evidence of intent. It is a pattern we notice after the fact because human brains are built to find patterns. Three-Eye Atlas did not pick its route, they will argue. It simply followed the combined pull of the Sun and the planets, and we happen to live in the brief era when that path cuts through our observational reach. That humility is important. It keeps speculation from outrunning the data. Yet the fact remains that this one visitor gives us a rare chance to watch how an interstellar body interacts with multiple gravitational wells and multiple radiation environments in a short span of time. By tracking its position before and after each encounter, and watching how its activity changes as it moves through different regions, we learn not only about the comet, but about the architecture of our own system. Whether the route is natural coincidence or something more, it functions like a grand tour in practice. For planetary defense experts and mission designers, that is a gift. It means they can test their models of how objects bend around planets, how small non-gravitational forces might add up along a complex path, and how tightly we can predict the motion of an active comet over many months. For everyone else watching from Earth, it adds a new layer of drama. Our mysterious, chemically odd, strangely resilient visitor is not just passing by once. It is weaving through our neighborhood like a tourist who knows exactly which landmarks to hit before heading for the exit. As the encounters unfold, observatories plan campaigns around each one. Jupiter for the deep gravitational tug, Venus for the harsh solar environment, Mars for the chance to look both from orbit and from the ground. That coordinated scrutiny turns Three-Eye Atlas into more than a curiosity. It becomes a moving test particle, a probe of the invisible structures that shape our cosmic backyard. And that, in turn, sets the stage for one of the most practical chapters in this story, where the focus shifts from what is it to how can we use this event to rehearse for the day when an incoming comet is not just strange, but dangerous. While the orbit plots of 3i Atlas were making theorists nervous and excited, a different community saw something else in that skinny curve looping around the Sunday. They saw a training opportunity. The International Asteroid Warning Network, a loose but very real coalition of space agencies and observatories, decided to turn this interstellar encounter into a rehearsal. The object itself was not on a collision course with Earth. That was the good news. The bad news, if you think long-term, is that one day something like it might be. Better to practice now, while the stakes are scientific pride instead of survival. Planetary defense starts with a simple but unforgiving requirement. You must know exactly where a threatening object is and where it will be. Not just tomorrow, but weeks or months from now. For solid asteroids, that challenge is manageable. They are compact and relatively predictable. Once you have enough observations, you can fit an orbit, propagate it forward, and be reasonably confident that a rock will be near a specific point in space, on a specific date. Comets, especially active ones, are a different beast. They shed gas and dust in uneven ways, like tiny thrusters firing at random points on their surface. Those small, continuous pushes can nudge them off their predicted paths over time. 3i Atlas is a perfect example of the problem. It has a bright coma that hides the real nucleus. When you point a telescope at it, you are not measuring the position of a clean, sharp point. You are measuring the center of a fuzzy glow. Depending on the instrument, the exposure time, and the processing techniques, that glow can look slightly different from night to night. Small differences in how observers define the center can translate into big differences in the calculated orbit when projected over millions of kilometers. If you are planning a mission to nudge such an object away from a future impact, that margin of error could mean the difference between a clean miss and a glancing blow. So the International Asteroid Warning Network announced what they called a Comet campaign built around 3i Atlas. The idea was straightforward and ambitious. For 2 months, from the end of November 2025 through late January 2026, observatories all over the world would aim at the same target, night after night. They would report their measurements of its position with as much precision as they could wring from their instruments. Then they would compare notes. Which telescopes and techniques gave the most consistent answers? How did different ways of defining the center of the coma affect the resulting orbit fits? Could new algorithms correct for those biases? This was not just a project for big national facilities. The planners explicitly invited skilled amateurs to participate. Anyone with a medium-sized telescope, a sensitive camera, and patience could contribute. That democratized the exercise. People in backyards and small observatories became part of a global effort to pin down an interstellar object to a fraction of an arc-second, an angle so small it is like measuring the thickness of a coin from hundreds of kilometers away. For many of them, it was the first time their nightly images were feeding directly into an international planetary defense test. The data pipeline ran both ways. Professionals shared improved ephemerides, the predicted positions that help observers point their telescopes on the right nights. Amateurs sent in their measurements, which were folded into the growing archive and used to refine those predictions further. Workshops and teleconferences buzzed with discussions about which tracking methods worked best when the object was low on the horizon, or when moonlight washed out faint stars, or when the comet's own changing activity made its coma swell and shrink. 3i Atlas became less of a mysterious intruder and more of a cooperative test pattern in the sky. Underneath the logistics was a serious question. Could the global system that would one day have to respond to a real comet threat actually coordinate fast enough, accurately enough, and broadly enough to matter? It is one thing to design a theoretical response plan on paper. It is another to herd dozens of observatories and hundreds of observers into a consistent measurement campaign, all while a real object is moving through a complex environment of solar radiation and gravitational tugs. If there were gaps in communication, software hiccups, or systematic biases hiding in the data, this was the moment to uncover them. As weeks passed, orbital solutions for 3i Atlas sharpened. The already low chance of any dangerous encounter with Earth dropped even further into the realm of impossible. In a sense, that was never the point. The value of the exercise lay not in proving that this specific comet was safe, but in proving that humanity could measure such an object with the necessary precision at all. every refinement in astrometric technique, every bug fixed in tracking software, every lesson learned about how gas jets alter a path would carry over to whatever object comes next. In that way, the interstellar visitor was already helping to protect the planet, simply by existing and being strange enough to force a new level of effort. The fear that wakes planetary defense experts at night is not only the thought of a big rock on a direct path, but the thought of a chaotic comet, bright and volatile, that refuses to stay exactly where equations put it. 3i Atlas offered a chance to chase that fear in a controlled environment, to move from vague concern to tested capability. By the time the official campaign window closed, the comet was heading outward again, fading slowly as it climbed away from the Sunday. The network stood down from its fire drill. Reports began to circulate about what worked well and what did not, about how much precision they had achieved and where improvements were still needed. The object itself continued along its hyperbolic track, oblivious to the fuss it had caused. And as it pulled away, attention began to drift from the practical matter of tracking toward a more expansive question. How many other wanderers like this are out there, slipping through the inner system unseen, each one carrying its own strange chemistry and its own potential lessons about how galaxies trade material, and maybe even the ingredients of life? By the time 3i Atlas was leaving the inner solar system behind, another realization was taking shape in the background. This could not possibly be the only object of its kind passing through our neighborhood. In fact, once you step back and look at the numbers, the idea that we have only seen 3 interstellar visitors so far says more about our blindness until recently than it does about how rare these wanderers really are. For most of human history, we simply did not have eyes sharp enough or fast enough to notice them. Modern sky surveys changed that almost overnight. Starting in the last decade, wide-field telescopes in Hawaii, Chile, and Arizona began sweeping huge strips of sky every clear night, comparing one image to the next to see what moved. Within a few years of those systems reaching full speed, Oumuamua appeared. 2 years later, Borisov, then 3i Atlas. 3 confirmed interstellar objects in less than 10 years, all spotted by a network that is still maturing. From that small but potent sample, astronomers have tried to estimate how many such bodies might actually be drifting through the inner solar system at any given moment. The answer is startling. There could be dozens, maybe hundreds, most of them too small or too dark to catch with present instruments. Soon, the Vera Rubin Observatory in Chile will join the watch. Its flagship project, the Legacy Survey of Space and Time, is designed to image the entire visible sky every few nights with unprecedented depth. That means fainter objects and faster movers will stand out more clearly than ever before. Some forecasts suggest that once Rubin is fully online, it might find 1 or 2 interstellar visitors every year. That would transform these events from freak accidents into a regular part of our observational diet. The sky would not change, our awareness of it would. Now fold that detection story into a bigger picture of how planetary systems evolve. When giant planets like Jupiter form and migrate within their birth disks, they act like gravitational slings. They scatter smaller bodies inward toward the star, outward toward the fringes, and occasionally upward into trajectories that exceed the escape speed of the entire system. Our own solar system almost certainly flung out a vast number of comets and asteroids during its early chaotic years. Other planetary systems do the same. Over billions of years, that process populates the galaxy with homeless debris, countless icy fragments wandering between, stars on paths that rarely but inevitably intersect with other systems. Each of those wanderers is more than just a cold rock. Comets in particular are loaded with complex carbon-based molecules. Spacecraft that have flown through comet tails or landed on their surfaces have found organic compounds, long-chain hydrocarbons, and even amino acid precursors. They are not alive, but they carry ingredients that can feed the chemistry of life on any world they strike or even graze. If interstellar comets are common, then so is the slow, constant exchange of such chemical cargo between stellar neighborhoods. This idea has a name in astrobiology. It is the notion that life, or at least the prebiotic chemistry that leads toward life, can be seeded across vast distances by natural processes. You do not need a directed mission or a purposeful act. You need only a galaxy filled with small bodies being traded back and forth over spans of time so long that human history barely registers. In that context, 3i Atlas is not just a curiosity that happened to wander through. It is a sample of a traffic flow that has likely been running since the first planets formed. Consider Earth itself. For 4.5 billion years, our planet has been bombarded by comets and asteroids from our own reservoirs, like the Kuiper Belt and the Oort cloud. If even a tiny fraction of those impacts involve material that had once been part of another star's debris stream, then some of the organic molecules in our rocks and oceans may have truly alien origins. They might have condensed in the cold outer disk of a distant star, been kicked out during a planetary reshuffle, drifted through the dark for eons, and finally collided with the early Earth, blending their chemistry with ours. Now, flip the picture around. Our solar system has ejected its own share of small bodies into interstellar space. Somewhere, out there, right now, there may be a comet composed of ancient solar system ice, making a close pass by another star. If that system has planets, and if one of those worlds has an atmosphere or a surface suitable for complex chemistry, a fragment of our own primordial material might already be buried there, waiting. We usually imagine interstellar contact in terms of radio messages or spacecraft. The quiet reality may be that we have been swapping molecules with unknown neighbors for billions of years without ever noticing. Seen in that light, 3i Atlas becomes less of a lone protagonist and more of a messenger from a vast, mostly invisible network. Its odd chemistry is a coded record of conditions in another protoplanetary disk. Its hyperbolic path is one thread in a tangled web of trajectories that crisscross the galaxy. Its very presence in our sky is proof that the space between stars is not empty, but full of slow movers carrying the physical memory of other suns and other worlds. There is something deeply human about how we respond to that revelation. Faced with an object like this, we immediately ask the big questions. Could life have started here with help from bodies like this? Could life that begins here someday spread outward in the same way? Are we watching a single comet, or are we finally becoming aware of a giant, ancient circulation system of rock and ice and organics that binds the galaxy together? 3i Atlas does not answer those questions. It simply makes them harder to ignore. And as it fades into the outer darkness, another shift happens in the story. The focus moves from what this one visitor can show us today to what its entire class of objects will teach us in the decades ahead, especially if we build the courage and the hardware to go out and meet them. Before we say goodbye to this comet, we need to look at what it will leave behind in our science and in our sense of place, long after it has crossed the orbits of the giant planets and slipped back into interstellar night. As 3i Atlas climbs back toward the outer darkness, the drama in the sky begins to quiet down. Its coma shrinks, its tails thin out. Night by night, it slides below the detection threshold of smaller telescopes. The fireworks show that pulled our attention away from our own planet starts to fade. Yet in another sense, this is the moment when its real impact begins. The photons are gone, but the numbers they carried are still here, frozen not in ice but in databases, hard drives, printouts, and in the minds of the people who watched. Astronomy is a slow art. What we see in one decade often makes full sense only in the next. Right now, teams all over the world are still teasing information out of the light 3i Atlas, reflected and emitted. They are refining orbits, comparing spectra, building and breaking models that try to reproduce the way it woke up, the way it threw off nickel without iron, the way its tail shifted shape and direction. Papers are being written, reviewed, argued over in quiet conference rooms and noisy online threads. Some conclusions will hold, others will not survive contact with future data. But all of it enters the permanent record, a baseline that later generations will return to. Imagine a young researcher 20 years from now, scrolling through archival data with tools that have not been invented yet. They will be able to pull up the brightness curves, the spectral lines, the precise positions measured during the planetary defense campaign. They will know things we do not, because by then Rubin will have catalogued dozens of interstellar visitors, and perhaps a dedicated mission will even have flown past one. Seen from that vantage point, 3i Atlas will not just be a one-off oddity, it will be the first detailed example in a growing family portrait. Patterns that are invisible to us now may leap out to them from the comparison. A ratio here, a temperature there, a shared quirk of chemistry that points back to certain kinds of stars. At the same time, planners and engineers are already folding the lessons from this encounter into mission concepts. Agencies have floated ideas for spacecraft that wait in deep space, ready to fire up engines the moment an interstellar object is spotted early enough. The dream is to launch not years after discovery, but while the visitor is still inbound, then meet it near its closest approach. 3i Atlas shows both the promise and the difficulty of that plan. Discovery in July. Perihelion in late October. In human terms, that is a blink. To intercept such objects, we will need hardware already built, funding already secured, and flight plans that can flex as soon as an alert comes in. On the ground, the planetary defense community has something more concrete than white papers. They have a successful fire drill. They know that amateurs can plug into global campaigns and that shared software tools can handle a surge of observations pouring in from every longitude. They know where the bottlenecks are in communication and where small improvements in calibration can buy big gains in predictive power. That may not grab headlines, but in the long game of protecting a planet, it is gold. When the next dangerous comet is discovered, some of the quiet confidence in our ability to track it will trace back to nights spent measuring this harmless interstellar stranger. Then there is the less tangible legacy, the one that lives in how we think. Before interstellar objects entered the scene, it was easy to imagine our solar system as a mostly closed system. We had our star, our planets, our comets and asteroids, and the rest of the galaxy stayed at arm's length. Oumuamua cracked that picture. Borisov widened the crack. 3i Atlas has blown it open. From now on, it is harder to pretend that the space between stars is empty. It is easier to see it as a slow, vast river of debris, carrying the fingerprints of distant suns right past our doorstep. That shift in perspective reaches beyond science. When you realize that wanderers like this have been drifting through our region for billions of years, you cannot help but wonder how many times they have brushed against our own story. How many carried organic molecules that ended up in ancient oceans? How many have we missed, simply because we were not looking? It also changes how we think about our responsibility. Our comets are out there too, crossing other systems, sprinkling bits of our primordial matter onto worlds we will never see. Even without radio signals or starships, we are part of a quiet exchange. 3i Atlas also leaves us with a more mature attitude toward the possibility of technology among the stars. The debate over whether its odd behaviors could hint at artificial origin has not given us a smoking gun. What it has given us is practice. Practice in framing wild ideas in testable ways without leaping to conclusions. Practice in holding low probability possibilities in mind, while still doing the hard work of improving natural models. 20 years ago, simply raising the idea that an interstellar object might be engineered could have been career poison. Today, scientists can publish careful papers that explore that space, and their peers will critique the methods rather than mocking the question. That is progress. As for the comet itself, it continues on, unchanged by our curiosity. In the next year, it will cross the orbit of Jupiter outbound, then Saturn, then drift past the realm of Uranus and Neptune. Eventually, it will be too faint for any telescope we have. It will become what it was before we noticed it, a dark fragment gliding through the galactic night, carrying grains and ices that remember a star we have never seen. Perhaps millions of years from now, it will have another close brush with a different system. Perhaps beings there, of whatever form, will watch it and ask the same questions we are asking now. In the end, that may be the most important thing 3i Atlas leaves behind. Not a clear answer to the question of whether it is entirely natural, not a tidy theory that explains every line in every spectrum. Instead, it leaves us with better tools, deeper archives, wider surveys, and a sharpened sense of humility. It reminds us that our models are only as good as the last surprise they survived, and that the universe is under no obligation to make sense on the first pass. We saw something strange. We pointed our instruments at it, we argued, we learned, and as it fades from our sky, we find that our curiosity has grown a little bit larger than our fear. For a species that is just beginning to lift its eyes from its own surface to the wider cosmos, that is no small gift.